Now, in the very last theorem of stratified random sampling, it is the comparison of variances between variance of proportional allocation and the variance of optimal allocation. This comparison is extremely simple. So we'll straight get into the proof. We'll first write the formulas of variance of y bar st proportional, that is 1 by small n minus 1 by capital N into pi si square, summation pi si square I is equals to 1 to k, and variance of y bar st optimum, is 1 by n summation pi si square minus 1 by n summation pi si square. This is whole square, by the way. This is whole square. I is equals to 1 to k. I is equals to 1 to k. Now all we have to do is find the difference between these two, and then we'll understand the with why proportional allocation is greater than optimal allocation. So variance of y bar st proportional minus variance of y bar st optimum is equals to, basically I will write it under, we'll also simplify this a little. We'll just multiply this value inside. So 1 by n summation pi si square minus 1 by n summation pi si square and minus of 1 by n summation pi si whole square minus 1 by n summation pi si square. Summation pi si square. If we multiply this minus inside, then 1 by n summation pi si square minus 1 by capital N summation pi si square minus 1 by n summation pi si whole square, right, plus, because minus into minus plus, 1 by n summation pi si square. Now this minus 1 by n pi si square and plus 1 by n pi si square will both get cancelled. Then 1 by n summation pi si square minus 1 by n summation pi si whole square will be the leftover terms. Now we, by a known formula, pi summation pi si is equals to s bar. This is one of the formulas in stratified random sampling. Then this would be 1 by n summation pi si square minus 1 by n s bar. 1 by n s bar. And in this term, if we take 1 by n common again, summation pi si square minus s bar, also whole square, by the way, because there is a square right here, so this would be whole square, s bar square, equals to 1 by n. What is this? Summation pi is equals to 1 to k, by the way. Never forget to put these limits. I always keep forgetting these limits. And this also can be written as si minus s bar whole square. This term can also be written as si minus s bar whole square. Sort of like how you can also write the variance and sample mean, where you can also write the squares inside and the squares outside as a whole square. We can write the same way here. The same way here. In stratified random sampling, Pi will almost always equal 1, by the way. The Pi will almost always equal 1. It will always equal 1. Then, in that case, this term will never become 0. This term will never become 0. It is always going to be greater than 0. This is always going to be greater than 0. Because there is also an n, and 0 divided by something will also become, well, it is basically undefined. So Pi is equals to 1. Then 1 by n summation Pi Si minus S bar whole square is, we can say, if also is greater than or equals to 0. It is greater than or equals to 0. Then we just proved that variance of y bar n proportional minus variance of y bar st optimum is equals to this. We just proved that the difference of these values is this. This is what we've gotten. And this value is always greater than or equals to 0. Then this value is greater than or equals to 0. And if we just switch the terms to the other side and we take the negative term to the right side, then variance of y bar n proportional is greater than or equals to variance of y bar st stratified optimum. That's it. That's all we had to prove. In this theorem, we have to remember a few basically hidden formulas in this entire stratified random sampling, where Pi is always going to be 1. Pi is always going to be 1, and summation Pi Si is equals to S bar. These are the formulas we have to remember in order to compare the variances of proportional and optimal allocation. That's it. This is what we had to prove, and that's what we proved. This is St. Sorry, this is St. This is also St. Y bar St proportional is greater than or equals to y bar St optimum. That's it.